Hi everyone, welcome to the last lecture for general chemistry. Congratulations on making it this far, and thanks for sticking with it through these online lectures. Alright, so we're on the last section then of the electrochemistry chapter, which includes batteries, corrosion, electrolysis, and practical applications of electrochemistry. So this is widely used in industry. You take advantage of this every day in your cell phone, etc. So let's get started. So first off, let's look at lead acid batteries. These are the sorts of batteries that are found in your car. If you have a golf cart, which I don't know if any of you do, I certainly don't, but your golf cart will have a lead acid battery as well. So the overall reaction is lead solid plus lead oxide. So we have lead in a zero valent state and lead in a +4 state. In a sulfuric acid bath, are making then lead sulfate. Now it's a +2 in both situations. So on the anode, we have our lead, solid zero valent lead. On our cathode, we have lead oxide. So the lead oxide is being reduced to lead sulfate. The zero valent lead is being oxidized to lead sulfate. So it's a little bit of a different reaction than we're sort of used to in our typical cells, but the guiding principles are the same. We'll look at these half reactions in just a moment, though. Alright, so the cathode side has a standard reduction potential of 1.685 volts, the anode negative 3.56 volts, and so to get the cell voltage, of course we just subtract the anode from the cathode, and we end up with the overall cell voltage of 2.041 volts. That isn't the appropriate voltage, however, for most vehicle systems, and so in order to get there, they attach these cells in series. When electrochemical systems are attached in series, meaning one after the other, the voltage is increased until you get to whatever value you're after. So if we have 6 cells in a row, we multiply 6 times the voltage to get our resulting overall voltage. In this case, about 12 volts for this battery. All right. So remembering, as we discharge a battery, the slope is fairly shallow because Q is not changing significantly. The concentrations of our reactants and products are not really dramatically different, the ratio of them, until we approach complete discharge. Once we approach complete discharge, the products overwhelm the reactants, and so we're getting very close to equilibrium. So there's not a lot of then ability to generate potential from that cell. We use in our cars, though, an alternator to keep the battery somewhere in this territory charged. That way we prevent total complete discharge of the battery. Alright, so here's a schematic of how these actually work. When the battery is acting as a galvanic or voltaic cell, ultimately to start the car, when we're going to be using this also to power our radio and whatnot before we get our car going. Well, we have then the anode, half reaction, and our lead solid, again being oxidized to lead sulfate, going from 0 to 2, so that generates 2 electrons. In this case, the other reactant is the dissociation product of sulfuric acid, so that HSO4 minus, then driving this reaction forward. So we also then now have the cathode side. Those electrons are flowing through our motor as we're starting up. We have then lead oxide, lead in a +4 state, going to lead sulfate now in a +2, also involving HSO4 minus from sulfuric acid, and again consuming then 2 electrons. So we have a complete circuit. We're able to then do chemical work on whatever system we're on, starting our motor, running our radio, that sort of thing. When the car is running, we typically then don't use the battery. It's only for the system is connected to the battery, but we're charging it then with the alternator. So we have the situation now where the anode is now the lead sulfate, becoming lead oxide. Electrons are flowing then from the alternator then to the cathode, which is our lead sulfate becoming lead, going from +2 to 0. So that's going to be a reduction. A red cat, don't forget that mnemonic device. And so it's going then from positive to negative as we are recharging. All right, so that's the basic premise of how a lead acid car battery works. The advantage of it is that you can charge and discharge the battery numerous times before it becomes fouled. An issue is overcharging or undercharging leads to the production of lead oxides that are not involved in the redox chemistry, so eventually you'll have a battery fouling. Also, if it's not perfectly sealed, that sulfuric acid can slowly evaporate, so eventually this battery will become fouled and it'll have to be switched out, but good battery technology allows multiple charge-discharge cycles. Alright, so let's look at lithium-ion batteries because they drive the modern era. So this lithium graphite plus cobalt oxide makes graphite plus lithium cobalt oxide. So we have cobalt in a +4 state going to a +3 state. We have lithium going from a 0 valent state then to a +1 state. So at the cathode, we have the reaction then involving we have an electron. It's reducing cobalt from cobalt 4 to cobalt 3 in this in our product here. At the anode, we have lithium graphite making graphite. It's producing an electron and lithium for an oxidation. So the lithium in this case is 0 valent, and over here it is now +1. That's where we're getting that electron from. The reaction in this case, or the actual construction of this cell, is completely different than the sort of simple cells we've been looking at, but the guiding principles then are the same. It's also worth noting that there are quite a few different lithium battery technologies where this cobalt oxide is switched for other metals like manganese or many other different types of technologies, and they each have advantages and disadvantages. Some of them can be more energy dense, but say less stable, like lithium batteries being very exothermic to the point of exploding is definitely an issue. So this technology has been settled on for now because it's reasonably energy dense and reasonably stable. Alright, so let's remind ourselves of electrical units in energy so that we can look at conversions or ratings on different types of batteries. So remember, current is charge over time, so however many electrons we're passing over time, and that is in units of amperes, which is the same as then coulombs per second, which is again charge over time. So an amp then has units of 1 coulomb per second. Chemical work or electrical work, however you want to think of it, joules are the units for energy, and they are coulombs times volts. So we can also then substitute in an ampere in this case, so an amp second times a volt is the same then as a joule. So you see how we'll be able to convert these different units to get at different properties of, say, batteries. Finally, power is energy capacity, or the energy delivery over time. That is in units of watts, which are joules per second, or amp volt. If you, again, want to just do these conversions, all these different units on these electrical energy units are helpful, different identities. Alright, so let's see how we can use these to ultimately look at battery capacity or other properties of batteries. Finally, then the more common unit that we see for power is the kilowatt hour, the power consumption of 1,000 watts for an hour. So it's, again, how we rate relatively large draws of power like we would see on our house. Alright, so let's look at an example problem. If it takes 6 seconds of discharge for a car battery to start the engine, and the starter drew a current of 230 amps, what mass of lead will be oxidized to lead sulfate in this time? So there's a few things we need to recognize here. We need to recognize that amps are, again, charge per second. We have an amount of time at 6 seconds, and so we can figure out then the amount of coulombs that must have passed during this time. Alright, so here's again the reaction. Lead solid, lead oxide. So we're going to see then what mass of lead here will be oxidized to lead sulfate, 0 to +2. Alright, so what we're after is the mass of lead, right? How much lead actually had to be converted. So we know then that it drew 230 amps for 6 seconds. So if we want to get rid of those units and change that into coulombs, because amps times seconds is equal to coulombs, so if we divide by seconds amps, we're now in units of coulombs. So this is how much charge was actually passed during those 6 seconds. We know that there are 9.65 times 10 to the 4 coulombs per mole of electrons. We know that there are 2 moles of electrons per mole of lead oxidized. And we know that a mole of lead weighs 207.2 grams, so we end up with our solution 1.5 grams of lead that was oxidized to lead sulfate to start our car. That's a pretty fast conversion of lead. Alright, so say then our alternator runs at 30 amps, typical value for a car alternator. How long will it take to recharge the battery with our alternator? Fortunately, our car isn't running at 230 amps for very long, basically just to start it up. But let's see what happens. So 2 then lead sulfate being again re-reduced to lead, so that requires 2 electrons, which are coming from our alternator. Alright, let's look at this solution. We're after how long this will take. We know that we have 1.5 grams of lead that was converted because we calculated it above. So how long will that take at 30 amps? We basically work this problem in reverse. So we go from 1.5 grams, convert that to moles. To reduce lead 2 to 0 valent lead requires 2 electrons. For every mole of electrons, there are 9.65 times 10 to the 4 coulombs. So we then want to change from coulombs to amp seconds, equivalent units right there. We know then that our current is at 30 amps, and so everything is canceled, and so all we're left with now are seconds. So it'll take 46 seconds. So it's pretty quick to get our battery charged back to where we were. Alright, so that's again how this cycling might work as in a pretty typical example. Alright, so that's batteries. Again, batteries can get very complicated in practice, although just looking at the half reactions can be pretty straightforward. Let's look at a really common then commercial application of electrochemistry, electrolysis and electroplating. So electrolysis is using an external current to drive a reaction backwards from the spontaneous direction. In fact, here we go. Providing energy to an electrochemical cell to drive a reaction in a non-spontaneous direction. So we're providing typically electricity to drive for those electrons to then go in reverse. Electroplating then is what we'll do when we are going to then plate out, say, an ion as a metal. Remember, we need electrodes to do any of this. We need an anode and a cathode. Oxidation is occurring at the anode, reduction at the cathode. Alright, and so if we then have the current in amperes and we have the amount of time, as we saw in the last slide, we can then get the amount of charge delivered, so the amount of electrons delivered to our system over time. Alright, those are our units. In this case, amperes times time equals coulombs, again from the last slide. So let's look at what we're going to use that for now with electroplating. Alright, electroplating are thin coatings of metal that can be applied using electrolytic reactions. So like chrome plating on, like say, your vehicle rims. If you want to plate out chrome, well, we need to take chromium ions in solution, plate them out as 0 valent chrome on our whatever material we're after. Alright, so here's an example of how this works. We'll again have ions in solution. In this case, we're making a silver spoon. On the anode side, we have just a 0 valent silver anode that's going to be slowly eaten away, become silver ions. As we're passing power through our system, our cathode side, we're delivering electrons from our power source, again typically electricity, at a regulated voltage. So those electrons are then going to reduce the silver in the water, and it's going to plate onto the spoon. So this is definitely a way that metals can often be purified from crude mining extracts. All right, let's look at this example though. How many grams of silver can be plated from a silver nitrate solution using a 200 milliamp current for 15 hours? So 200 milliamps is a relatively feeble discharge, something like we might have on a little bench top system. All right, so let's remember what reaction's actually involved. This is a pretty simple half reaction. Silver plus one electron makes zero valence silver. So it's being reduced, our oxidation number is going down. So what are we after? Grams of silver, mass of silver. We have 200 milliamp hours, so that's 200 milli is of course 10 to the minus 3, so 200 times 10 to the minus 3 amps. We use our unit identity for amps are being the same as coulombs per second. So then we'll take our value for 9.65 times 10 to the 4 coulombs per mole. So we know then for every mole of current, 1 mole of electrons, we can reduce 1 mole of silver ions to silver metal. 1 mole of silver metal weighs 107.9 grams. We know then 1 hour, just to get to the appropriate units, is 3,600 seconds. We have 15 hours, and so we can plate 12 grams of silver. So again, typical for a benchtop sort of electrochemical cell. So on an industrial scale, like copper plating, they'll use much higher currents and again much larger physical systems to plate out a whole lot more than that. All right, so one thing to note real quick, the actual reduction potential in this case does not matter. It's plus 0.8 volts, but that doesn't appear anywhere in this equation. We don't actually need the standard reduction potential of that reaction. We just need to be able to overcome that with our power supply. All right, so in electrolysis then, let's look at another example. Magnesium metal can be produced by passing an electric current through molten magnesium chloride. So this might be the way that magnesium metal gets produced industrially. So the reaction will look like the following. You have magnesium ions, again, as liquid because they're molten, plus 2 electrons is making the zero valent magnesium liquid. All right, so that has a standard reduction potential, negative 2.37 volts, but again, as we saw in the last slide, that's actually not relevant. This is, though, a half reaction. For gaining electrons, this is being reduced. We're going down in oxidation number, so it's a reduction reaction. Reduction occurs then at the cathode, a red cat. So there we go, we've solved that. So how many grams of magnesium are produced if an average current of 63.7 amps flows through magnesium chloride? All right, so we've doubled the amperage, but magnesium, though, we have to put 2 electrons on it in order to get it to zero valent magnesium. So let's see what that looks like. All right, we're solving for the mass of magnesium that we can plate out. Here's our amperage, 63.7. We use our identity that 1 amp is the same as a coulomb second. So 9.65 times 10 to the 4 coulombs then per mole of electrons. And then we have, again, 2 moles of electrons are required to reduce 1 mole of magnesium down to magnesium metal. So 1 mole of magnesium has a mass of 24.305 grams. And we're doing that now. We're passing this amount of current for 4.5 hours. And we're in units of seconds from all the way back over here. So we need to convert from hours to seconds. And so we're left then with our solution of 130 grams of magnesium. All right, so you might, again, if you're actually plating this out depending on how practical it is, you might use a higher amperage just to get that reaction to go faster. All right, so here's the interior of a copper electroplating facility. We have these sheets of copper that have just come out of the electroplating bath. So our electroplating bath contains copper ions, passing electricity through it, and then on the cathode we have the deposition then of this zero valent copper that's been reduced from copper to in solution. So again, this is the way that copper is typically purified from crude ore. It's dissolved and then plated out. All right, so let's look at a thing that is actually a major industrial focus, corrosion and rusting. People spend a huge amount of time and effort trying to prevent corrosion and rusting. It'll often lead to the fouling of certain systems and it can cost a whole lot of cash for certain industrial processes. Alright, so what is rusting? Well, it's the oxidation of a metal by oxygen. Remember, oxygen is a very strong oxidant, partly why it's named that. And typically for many metals, moisture can enhance it by providing a slightly different reaction, by a hydrolysis reaction in place of just an oxidation. Alright, here's a simple depiction of a rusting system. We have zero valent iron metal here in gray. We have a water droplet on our metal surface. This can happen with water vapor in the air as well, but it's just easier to see with water, with just a bubble of water there. And we have our growing rust deposit here. So what's happening at the cathode, we're reducing oxygen with either protons or water, depending on our situation. We're reducing that to water or hydroxide. Meanwhile, the other half reaction on the anode is that zero valent iron is being oxidized to iron 2. This is a little bit of a complicated process. It can be oxidized directly to iron 3. Typically, the actual rusts themselves have iron in a plus 3 state. So as we see here, Fe2O3, iron must be plus 3. And so that oxidation can happen all in one step from Fe to Fe3, or it can be oxidized to Fe2 in the water layer or in, say, even water vapor layer, then rapidly hydrolyzed then to Fe3. In either case, we get these rust deposits, which are iron oxides or oxyhydroxides, just depending on the conditions in which they formed. And they can actually have both. You can have a mixture of oxyhydroxides and oxides. That's why there's this X here. It's certain amounts of water in the structure. Alright, and so this reaction is spontaneous and explains then why your car rusts but doesn't unrust. So this reaction is always occurring. If your car is painted, you're preventing the delivery of both oxygen and water to your car. So getting a big scratch on it can be a fine place for rust to start forming because you no longer have that protective paint layer. Also, many of the materials they're going to use in cars are going to be a little bit more rust resistant today than they used to be. Things like alloys, as we'll see in a minute, can prevent rusting. But in any case, this isn't always going to be spontaneous in the atmosphere. The equilibrium lies far to the right, and we also have a large abundance of oxygen in the atmosphere driving this reaction. And so we'll again always rust but not unrust. So you could take this car and with some complicated or some technical caveats and actually unrust it by using the electrolysis method. Might not come out good as new, but you can at least drive this reaction then in reverse by applying again a current. I don't know if it'd be worth putting this in an electrolysis system and trying to get that back to the zero valent metal, but hey, it could be done. Alright, so let's look then at preventing corrosion. So again, that's a really a major industrial focus. So there's a few methods. First is we have a material called galvanized steel, which is where zero valent iron is dipped in typically liquid zinc, and so we have a zinc coating on the outside. That zinc is rapidly oxidized to zinc oxide. That zinc oxide is effectively the same as having a paint layer on a car. It prevents further penetration of oxygen to that zero valent iron, preventing it from rusting. If you cut a galvanized steel like nail in half, that iron is now exposed and it can oxidize from the inside. Alloys are another way that we can prevent corrosion. By adding metals like chromium or nickel to our iron, we can then have those metals form oxides. Those metal oxides can again form sort of a protective coating around our iron and prevent it from rusting. So there are different formulations of stainless steel. You'll see like 304 or 316, and in those cases you just have different ratios of chromium and nickel and different other metals then to get to that technical specification. Alright, and then another common thing that's used in tankers and underground buried tanks. You don't necessarily want to have to paint an underground storage tank, say to store gasoline. It might eventually still rust and go away. And so what's done in this case then is there a concept called a sacrificial electrode, where you have a sacrificial metal of zinc or magnesium. It's ultimately attached then to that steel tank. It's buried underground, and then that undergoes oxidation rather than your actual tank. And so that's all fine and good because you don't care about it. All right, so that's again a major way that corrosion can be inhibited. There are many other methods, but that's just the very basics. Finally, one other application that's gaining a lot of research attention, as it should, are fuel cells. Fuel cells are voltaic devices in which there's a constant flow of fresh reactants to the anode and cathode, so the reactants are not depleted. So the most common example is going to be like a hydrogen fuel cell, where we're delivering hydrogen gas from a storage tank, combining that with molecular oxygen from the air in order to generate water. So that's going to be a very exothermic reaction. We're going to be able to use that to drive or to generate a current to drive a motor. So the hydrogen fuel cell uses streams of, again, hydrogen and oxygen gas that diffuse to the following anode and cathode reactions respectively. So again, we're pumping hydrogen in, it's producing electrons and forming acidity. We're again taking oxygen from the air, combining it with some of that acidity, combining that then with electrons, reducing that to water. So the overall reaction is pretty simple. 2 hydrogens plus O2 makes then 2H2O. That has a cell potential of 1.229 volts. So this is conveniently the reaction that we use to send stuff into space. It's very, again, thermodynamically favored. This is going to happen, and so we're taking advantage of that in a fuel cell to generate the electrons. So in this case, then we have 2 times H2, so we'll have a 4 electron transfer to make all of this happen. So here's a diagram of how that looks. We have our hydrogen side of our fuel cell over here. We have our cathode side with oxygen on this side. So again, that hydrogen is being oxidized ultimately to water. Oxygen is being reduced to water. We have a flow of protons across our proton exchange membrane and a flow of electrons then from one side to the other. So again, a little bit more of a complicated setup than our simple voltaic cells from before. But again, the guiding principles are about the same. So we have our actual then electrodes doing the work. We have, again, this O2 minus intermediate state combining with protons to form then H2O. So this water vapor then is our output. So that's a convenient, environmentally friendly output there. And we can again use that current to drive a motor forward. So a lot of research is going into these that are practical prototypes out and about now. As far as the availability of hydrogen, well, that's going to be your biggest challenge right now. All right, so that is it for this chapter. Here's just another listing of this standard reduction potential table. So thanks again for tuning in. Good luck studying with your exams, and thanks again for adapting to this online learning environment. I know no one really wanted to be doing it this way, but here we are. All right, as always, let me know if you have any questions, and we'll see you soon. Thanks.